So for our first video for Chapter 2, I'm going to talk about some of the basics of the structure of an atom. I'm also going to start talking about mass symbols and nuclei. So an atom has a small, dense nucleus in the center, and then it's basically surrounded by a large area of mostly empty space, known as the electron cloud. Now, to give you an idea of just how much of an atom is empty space, this nucleus, let's say if the diameter of an atom was the diameter of a football field, so let's say we're at the Bill Stadium, and we blew up an atom to be as big as the Bill Stadium, the nucleus would be about the size of a blueberry, and the rest of the space is basically empty. And actually, all matter is made up of atoms, right? So actually the vast majority of all matter is empty space, as it turns out. It's kind of a mind-boggling thought to try to process, but it's true. Now the center of the nucleus has two subatomic particles. And when I say subatomic, all I mean is it's just subatom, just smaller than an atom, right? So there are three main subatomic particles that you'll have to focus on. Two of them exist in the nucleus. The first one are protons, and protons have a positive charge. You can remember that because proton P, positive P, right? They both start with P. The other particle that exists are neutrons. And neutrons have no charge. They're neutral. Neutrons, neutral. Now, with charges, you might know the phrase that opposites attract. Right? So if you only have either positively charged things or no charge in the nucleus, you don't have any negatively charged particles in the nucleus, how do they stay together? Well, there are four fundamental forces of nature, and the strongest one is the strong nuclear force. And that's actually the force that keeps these together. It keeps the nucleus of an atom together. And now, protons and neutrons are approximately the same size. Technically, they are slightly different, but in terms of sig figs, the difference is minute enough that we consider them to be the same size. So we say that they're both 1 AMU. An AMU stands for atomic mass unit. Right? And they're both protons and neutrons each count for 1 AMU. Now, in the empty space around the nucleus, you get electrons. Right? So electrons, and they're constantly moving around very, very fast. And that's the third subatomic particle. Those ones are negatively charged. And electrons weigh 0 AMU. Now, of course, technically they have mass, right? And if they didn't have mass, they wouldn't exist as matter. But they are so much smaller than protons and neutrons that, in terms of any kind of level of sig figs, the mass is so insignificant and so small that it's irrelevant. So we effectively say that they have 0 AMU. Alright, so with that, I want to talk about mass symbols. So mass symbols are a way to represent elements and talk about some of their subatomic particles. So the general notation for a mass symbol is this: X, M, and Z. So this X, that represents the chemical symbol, or the atomic symbol. And that's what you see on the periodic table. The 1 or 2 letter abbreviation for each atom, that's represented here by this X. This M, now sometimes you'll see this as an A, but I put it as an M just to make it hopefully a little less confusing. This is something called the mass number. So this is your mass number, and Z is your atomic number. What are these? Now, the atomic number that's the number that your element is on the periodic table. So, now, I will say, one thing to keep in mind, periodic tables do not follow this same notation. So you won't always see these things in those exact positions on a periodic table. So whatever the number of the element is on the periodic table, that is its atomic number. And the atomic number is just the number of protons. So what that means actually is that the number of protons determines the identity of the element. If you change the number of protons, you will change the actual identity of the element. So for instance, carbon is number 6 on the periodic table. That means that every single element of carbon in the world, no matter what you do to it, no matter what else, as long as it's still carbon, it will always have 6 protons. If it no longer has 6 protons, it's no longer carbon. Okay? So the number of protons is the only thing that actually determines the identity of an element. Mass number is the number of protons plus the number of neutrons. So that's all of the so the mass number just tells you how many subatomic particles exist in the nucleus. So if you're trying to find the number of neutrons, you can just do the mass number minus the atomic number, because that's the protons and neutrons minus the protons. So again, for carbon, let's say the X would just be its chemical symbol, which is C. Its atomic number 6, and let's say for this one we have a mass number of 12. So that means that you would have 6 protons, and 12 minus 6 means 6 neutrons as well. And that actually leads me to something called isotopes. So isotopes these are atoms of the same element but different mass numbers. So if they're the same exact element, that means that they have to have the same number of protons. But if they have different mass numbers, and mass number is protons plus neutrons, what has to be different about them? Neutrons. So isotopes are atoms of the same element that have different numbers of neutrons. And what's important here is that if you look at the periodic table, the masses on the periodic table, a lot of those are decimals, right? And you might say, well, if you're just adding whole numbers of protons and neutrons, how can you get a decimal? And the reason is because on the periodic table, you're not actually looking at the mass number. The mass number is for a single specific atom that you're talking about. This is something known as the atomic mass. And the atomic mass is basically a weighted average of all of the different isotopes of every atom in the world. So for instance, let's say for chlorine. Chlorine has 2 isotopes. So we've got chlorine. I'll put its atomic number here. So we've got chlorine 35, which means it has a mass number of 35. And we have chlorine 37. So these are 2 naturally existing isotopes for chlorine. They obviously both have to have 17 protons, which means that 35 minus 17 is 18. So this version has 18 neutrons. 37 minus 17 is 20. This version has 20 neutrons. And we also know the percent abundances of these. If you know the percent abundance of different isotopes, you can figure out the atomic mass. So the percent abundance, so basically what that means is out of all of the chlorine atoms in the world, based on data that's been collected, what percent of those atoms are each individual isotope. So obviously they should add up to 100, right? So the percent abundance for chlorine 35 is about 75.77%, and the percent abundance for chlorine 37 is about 24.23%. So if you're trying to figure out the atomic mass, basically what you can do is take the percent abundance for each isotope, convert it to a decimal, multiply it by its atomic or by its mass number, and then add those all together. So what do I mean by that? Well, first of all, how do you convert a percent to a decimal? You have to divide by 100. So dividing by 100 is the same thing as moving the decimal over 2 spots. So 75.77 written as a decimal is 0.7577. Right? It's the same number, just a percent decimal form. So you multiply that by the mass number of its relative, isotope. Right? Put that in parentheses. And we just do the same thing for this one. Convert this to a decimal, so we've got 0.2423 times its mass number, 37, and just add those together. And no matter how many different isotopes you have, it doesn't matter. You can do this every time, and it'll give you the correct answer. And our final answer would be 35.48 atomic mass units. And that would be the atomic mass for chlorine based on this data.